All right, we'll go ahead and get started. Hello, welcome everyone. Thank you for joining us today for the Embodied Carbon Network's 2019 webinar series. My name is Tina DeLeggi. I'm a program manager at the Carbon Leadership Forum, and in this role, I help manage the Embodied Carbon Network. Today is the first session of a six-part annual webinar series. We have several exciting speakers joining us today who are going to discuss insulation material choices and related challenges and opportunities to measure and reduce environmental impacts. Please note that today's session will be recorded and made publicly available upon its completion. So many of you joining us today are already Embodied Carbon Network members, but we invite people inside and outside the network to join these webinar sessions. So I invite you all to learn more about and join the network. So the Embodied Carbon Network is a communications and knowledge building platform that was started by the Carbon Leadership Forum about 2 years ago in January 2017. The network is bringing together over 440 professionals from across the building industry, academia, nonprofit, governments, and other groups, resources, engage in discussion, and help develop educational content such as these webinar series. So the network has evolved into a vibrant, engaged global community from members representing over 110 cities across the world. On the ground, our work is quite varied, from focusing on data and tools to advocacy, outreach, education, research. But here we are brought together under a shared mission to eliminate embodied carbon emissions from the building sector, especially in order to meet global greenhouse gas emission targets by 2050. So the Embodied Carbon Network comprises 10 subject-specific focus groups, which members can join for more focused engagement around a topic related to embodied carbon. So the Embodied Carbon Network, again, is funded and managed by the Carbon Leadership Forum. The Carbon Leadership Forum, led by Kate Simonen, is an industry academic collaborative based out of the University of Washington that carries out research, education, and outreach initiatives focused on LCA and embodied carbon emissions tracking and reduction. So thank you to our CLF sponsors for supporting the network and the annual webinar series. So again, today's session is part of a six-part series, and each topic is based off the network focus group subjects, and our focus group chairs are working with groups to develop content, identify speakers, and help deliver the series. So our goal is that each session will not only be useful to live participants, but also serve as free educational resources for anyone else who's interested in learning more about this topic. So please feel free to share the webinar recording with your colleagues, professional networks, and students. So just a quick note that we have a lot of different speakers who are joining us throughout the year, who are going to share their own work, knowledge, and research. But this doesn't necessarily represent other members who are within the Embodied Carbon Network or the network or Carbon Leadership Forum. So before we dive in, just a few quick logistical reminders. We have 3 presentations today that will be followed by 10 to 15 minutes of a question and answer session. So if you have any questions throughout presentations, please use the Zoom chat function to submit any questions or comments that you have, and we'll try to direct these questions to the appropriate speaker after presentations. So these sessions, the live sessions, are eligible for AIA continuing education credits. So if you're an AIA member and attending the live session, please send me your full name and your member number to this email address, and then I'll make sure that, that you get credit for this. So we had a ton of great sessions last year throughout 2018. So if you missed any of these, you can go back and listen to recordings on the Embodied Carbon Network webpage. And just save the date for the next webinar, which will be on May 17th at 9 a.m. Pacific time, and led by the Policy Focus Group. So now I'm gonna hand off to our materials focus group chair, Dave Walsh. Dave Walsh is a registered architect and director of sustainability and design integration at Sullivan Construction. So Dave's gonna kick us off and introduce you to our speakers today.
Thanks, Tina. Good morning, everybody, and welcome to this webinar that's hosted by the Materials Focus Group. Today we're talking about insulation, which is kind of a unique material because it participates both in the operational carbon and the embodied carbon story of the building and over the life cycle of the building. We have three great speakers today that can talk about the role that insulation plays in overall embodied carbon. And we'll talk just a little bit about some different types of insulation. It's obviously a subject that there's a wide range of material choices there, but today you'll hear just a little bit about some of those choices. So our first speaker is Christian Kofod, the Sustainability Manager at Rockwool and Rockfon North America. Ever since graduating as a chemical engineer in Denmark, Christian's career has revolved around sustainability. After a brief stint working with life cycle assessments within a wide range of industries, Christian has focused primarily on building products. First with the wood technology at the Danish Technological Institute, where he was involved with both Product Emissions Laboratory and the Danish Indoor Climate Label. Following a number of years representing the Danish woodworking and furniture industries, Christian joined Rockwool Group in Denmark, first working in public affairs and sustainability for the global Rockfon acoustic ceiling tile brand for 8 years, before taking a position as sustainability manager for both Rockwool and Rockfon North America in 2017. Christian has worked all over the world with sustainability documentation of building products and with many global and national green building schemes. Christian has also worked with EPDs in Holland, Norway, Germany, France, the United Kingdom, and North America, and with various product emission testing protocols on multiple continents. Much of Christian's work in North America focuses on material transparency, supporting healthy indoor environments without unwanted indoor pollutants. He's based outside of Toronto, Canada, supports all of Rockwool's and Rockfon's North American businesses. Our second speaker is Chris Magwood, who is currently the director of the Endeavor Center. The school runs 2 full-time certificate programs, Sustainable New Construction and Sustainable Renovations, and he hosts many hands-on workshops annually. Chris has authored 7 books on sustainable building, is the co-editor of the Sustainable Building Essentials series, and is the past editor of The Last Straw Journal, an international quarterly of straw bale and natural building. He has contributed to articles in numerous publications on the topics related to sustainable building and maintains a blog entitled Thoughts on Building. In 1998, Chris co-founded Camel's Back Construction, and over 8 years has designed or built 30 homes and commercial buildings, most with straw bales and often with renewable energy systems. Chris is currently completing an MA at Trent University. His thesis, Opportunities for Carbon Capture and Storage in Building Materials, will be published in April 2019. Chris is an active speaker and workshop instructor in Canada and internationally. And finally, our last speaker is Pamela Bosch, who is the founder of the Highland Hemp House, which is a residential project in Bellingham, Washington, which has been built to demonstrate the merits of hempcrete. A generalist task, this venture has involved advocacy, education, experimentation, and numerous trips to Europe, where building with lime and bioaggregates are better understood. To be completed by 2019, Highland Hemp House will be a demonstration house to inspire rapid implementation of the code and building communities. It will be made available for field study and consultation to demonstrate that natural building products can achieve healthy and efficient indoor environments with high carbon capture, building longevity, and aesthetic integrity. Ms. Bosch considers it her legacy project. So with that, we will start with our first speaker, Christian. And Christian, go ahead and take control of the screen, please.
Thank you very much, Dave. Let's see how this works. Thank you for that presentation. My name is Christian Kofod. to maybe answer some questions, I'm from New Zealand originally. I spent most of my life in Denmark. And now I'm here, so my accent's a bit screwed up, and sometimes so is my spelling sometimes. So bear with me, please. I'm coming through, Dave. Sound-wise?
Yes.
Good,
Yeah,
excellent.
sounds great.
So this is not so much presentation on Stonewall. If you want a Stonewall 101 and how amazing a product that is, please reach out, and we can maybe do that at a later stage, or maybe in Rockwell could host a seminar. So now I'm just trying to change. So Rockwell is a company based out of Denmark. We have been making Stonewall insulation for the last 80 years. Well, make that. Sorry, I can't get rid of this sidebar. I don't know if you can see that. We have 40 factories worldwide, approximately, and 10,000 employees. In North America, we've been here since the 80s. Our headquarters in North America is out of Toronto. We have a factory in British Columbia and a factory in Mississippi also. Apart from making insulation material, we also have an acoustic division, Rockfone. We have two factories, one out in Baltimore and one in Chicago, and they make the metal parts for our ceilings. Rockwell is primarily insulation, so, but we make so many more things. So we have our technical insulation, which is for the process industry, a very interesting product. Then we have the fire-safe insulation, the insulation which we use in buildings, which most of you hopefully know. We also have our core solutions products, which is for OEM, where our products are used by other manufacturers to be included in their products. But apart from just making insulation, we also use Stonewall fibers for other products. We have our Lapinus division, which makes specialty fibers, for example, for brake industry, but they're also now working on how to make solutions for areas that see floodings. A very interesting product we have there. We have Grodan, which is used in greenhouses for hydroponic purposes. We can save up to 50% of the water used compared to soil. We have Rock Panel, which is building cladding. We don't have that in North America yet. And then finally, we have Rockfone, our acoustic seating tile division. Basic for all of this is, of course, the stone that we use in all these products. Our products are very, if we look at the insulation products, they are very flexible. We use them for many different areas inside the building, both the low density products, residential interior products, loft partition walls, etc. And then we can go to the very high density products, the rigid products, which can be used in the building envelope, flat roof facade, foundation, sandwich panels, and whatnot. And again, it's all based on the same process. It's all stone wool based. And this is why we do it. We have an impact, of course, when we make our products, but it's the emission and the energy used by our products is saved 85 times during use, installation of the products. The technical installation for the process industry is even more impressive, how much energy that can save. A lot of industries still don't think of insulating their process equipment, but there are huge savings to be reached there. We're in it for the long term, and I think this is what I really like about our products. So we tested some of our products that were installed in the 50s, and later we took them up a few years ago and measured on, hey, how are they functioning after they've been in use for 50, 60 years? And we can see now that they still deliver the same functionality as they delivered where they're installed. And I think this is actually the best picture of how we perform, also sustainability-wise, that will continue to add to the buildings. Our products primarily are designed so they don't absorb water. We don't want them to absorb water in buildings, but we can re-engineer them so they absorb up to 95% of the water which comes into the product. which is used, of course, for the hydroponic, but also for these products which are used for water management. So it's all stone, but it's quite amazing what we can do with it. This is our process. We'll make our products. Basically, we have raw material, primarily stone, basalt stone, and we will also mix this with melt. We put it through our copper furnace, or we have other types of furnaces too. We have a spitting chamber where we make cotton candy, if you will, out of stone. We add binder and some repellency agents. We cure it, and we cut it, and that's basically how you make stone wool insulation. It's not rocket science, but still it sort of is. We recycle our waste internally. We use recycled material from other industries as well. Not so much in North America, but in Europe, where distances are smaller and where we have a lot more factories, we take waste from a lot of other industries. And this is, I think, one of the cornerstones in the work we're doing. We're really looking how can we reduce the waste from our factories. We have a goal to reduce 85% of the landfill that we send to waste. We can use it ourselves. There's no reason to send it. When the products go into the buildings, if we can get it back, we will do that. We have in some countries, in mature markets, we do have recycling offerings where we take it back after end use in buildings. In North America, we just last year launched our OEM recycling service. So we do take some waste back from customers. As I said, we melt stone, so the main embodied carbon is emitted during our production process. This is from our NIMA, so the North American Mineral Wool Association EPD, just launched last year, or republished last year. We had an older one. And not surprisingly, the main impact comes from the production, the manufacturing of the mineral wool. 10 minutes is way too short time to give this presentation. Well, this is how we work in Rockwool. So we have our main EPD experts sitting in Denmark. They work primarily through EBO in Germany. And from the countries that we have mutual recognition, then we have our EPDs sent through there and recognized in different countries. For North America, we are just finalizing our product EPDs, and we're trying to make this as simple as possible. So we'll make one EPD with scaling factors, and that will cover 99% of all our products. Hopefully you recognize some of the names here. We want to make it easy for our customers to find all the information. So here is our website where you can find more if you want to know. We have Declare, Green Guard, EPDs, and whatnot. If we look at our materials, we are seeing a lot of comparing materials for materials. Insulation materials, they are always part of the system and should be compared in situ. And I also think that they're inherently different, and we tend to forget that sometimes when talking about embodied carbon. This list links to fire resiliency, durability, the chemical footprint, and vapor diffusivity. Some materials are closed, some are open, and they work differently, and they have to be, other materials have to be included. If we look at different materials where we look at EPDs, we see big variations between these materials. These are some examples, and what I noticed here which really made me wonder here, was steel and recycled steel. The big variations in the recycled steel was you could actually here choose a steel material which had a lower carbon impact than a recycled material. And for me, that highlights some of the challenges that we have working with EPDs and getting these numbers. Are we choosing the materials which actually are best in class, or are they simply calculated smarter? I can see from the work that we're doing that you actually can calculate quite smart and get some values that are lower than what you should be showing. Some work has been done on comparing different EPDs for insulation materials, and we've seen that what this work showed was there were a lot of EPDs. Out of 12 EPDs, 83% of them actually did not fulfill the requirements, the ESO requirements, even though they say they do. And especially that's linked to the boundary definitions, where it's 10 out of 12 that did not fulfill the requirements. Also been looking at another study where they looked at 66 different EPDs. out of 4 that used the mineral wool, the same PCR, only 2 of them could actually be compared. Which surprised me was that 5 that used different PCRs actually could be compared, were valid to be compared. So even though we're using the same PCRs, it does not mean that we can truly compare the EPDs and compare the global warming potential, the carbon footprint, if you will. We are seeing more focus on facility-specific EPDs, a requirement for that. Just a word of warning, it is impossible for many manufacturers to make these facility-specific EPDs and deliver them. We cannot guarantee that the products will be sourced from a specific facility. And also, when we look at our raw materials, we have very limited access to specific data for that. That is all based on averages, and the facility-specific EPDs will not give the granularity which is expected. And of course, there's a cost. It costs about at least $40,000 to make an EPD. And every time we have to make one, it will have an impact on the price of our products. I'm going to skip this because I'm running out of time. But final comment, I think it's really great that we are seeing this focus and an interest in our EPD and our carbon footprint. Sometimes it's been challenging for me in my position to go to our company and say we need to spend money on this, but with increased focus from customers, our company has more of an incentive to work with this kind of data. I'm worried with the large degrees freedom for program operators to develop PCRs and do the data. Some of the PCRs that some of the EPDs I mentioned before that were not comparable. One of them was the NIMA EPD, which we were involved in, the earlier one, and that actually does not fulfill the requirements. And we as a manufacturer don't have the knowledge, the insight to challenge our program operators if they are doing the EPD correctly. And I also question how mature the science is behind these when we get our data. There's a lot of variation. There's a lot of work we have to do. I think we've done some great steps, but for sure, I can see that there are a lot of challenges for us to get better at looking at how we collect our data, so we truly can compare, and we're more precise in how we compare, and we can use it for making true decisions and choosing the best products for us. Costs, I've said that, and then I think we have to be aware of the rabbit holes. Carbon emissions, global warming, of course, is one of the biggest challenges for our generation. And we really have to work with this, and I think this work is great. But we also still have to remember maintaining a holistic approach, toxicology, end of life, fire, indoor air quality, and so on. And I'm going 1 minute over. Sorry about that. One last ask for people listening in. If you have questions to our products, please go to the manufacturer, in this case, me or Rockwell, when you have products to our questions, or questions to our products, sorry. We are seeing a number of our competitors or other materials making claims about our products which simply are not true. So please come to us if you have information, questions to our products, and we'll be happy to ask them. Thank you very much. Sorry about I ran over.
Christian, thank you very much. That was great. And now we will transition to Chris Magwood, kind of moving from looking specifically at a material and taking maybe a larger focus on the building and seeing how insulation and other materials interact over the life cycle.
Okay, well, thank you very much. And it was great to hear Christian's presentation. I've been living and breathing EPDs for the last 3 years of my life, and I certainly appreciate lots of the insight from the manufacturer side, and have spent a fair bit of time, considering the comparability, and that really informs the study. So what I'm going to present is a study I've been working on to basically look at 2 types of residential buildings. Larger multi-family building, an 8-unit building that you can see on the screen there. It was used as a model, and a smaller single-family residential building of about 2,000 square feet. So for this study, what I wanted to do was take these 2 building typologies and look at them with a few different material assemblies. I actually did over 100 different material assemblies, but for this presentation, I'm going to look at 4 of those. And taking those 4 assemblies and looking at them at 2 different levels of energy efficiency, which I'll get into later. We also created energy models for all of these buildings, and then we're able to sort of look at both the embodied carbon side and the operational side, and what those 2 look like between now and 2050. So just a few more parameters about these model buildings. The floor area was kept constant for these. So as different insulation assemblies were used, obviously some walls needed to be thicker to achieve the same R values. All the R values that we used are there on the screen on the right for you. The code compliant ones that are marked with CC are designed to meet the 2019 Ontario Building Code minimum efficiency standards. And then the high performance ones, we sort of did a survey of people doing high performance buildings in Ontario, and this is kind of an average type snapshot of what they're doing in terms of improving those R values. So in the study, I modeled well over 300 different materials that could be used, and you know, all of them actually are being used for residential buildings in this part of the world. And as Christian was saying, you know, you don't want to just make up models or compare materials that don't actually work in a building or don't work together. So of the 4 assemblies I've chosen to look at for this presentation, they all really reflect current practices. There are, you know, builders building in these ways here and now. So they're very relevant to how low-rise is being built in this part of the world. And for my sources of data, wherever I could, I was using industry average EPDs for North America. If there were products that didn't have an industry average EPD, I found as many specific manufacturers' EPDs, and I averaged those. If there was no North American data at all, I would look for an industry average EPD from Europe. And then again, if that wasn't available, an average of product-specific EPDs from Europe. And if none of that was available, I would go to peer-reviewed LCA data, and I never used less than 3 LCAs. And so again, those were averaged. So, you know, sort of trying to take a snapshot, not of comparing a particular product or manufacturer, but of product types and material types. So the 4 buildings that I'll focus on for this study, on the left, the highest carbon model, you can sort of see what some of the materials were in the makeup of that. So I was looking at foundation insulation, exterior wall assemblies, the cladding on the exterior, interior wall framing and cladding, windows, floors, and floor framing, roof and attic insulation, and ceiling and the actual roofing materials. So the highest carbon model, basically I picked the materials that had the highest carbon in that category. And again, not trying to just pick ones. There were some that I left out because they aren't really things that people use commonly. The moderate carbon one was chosen, those assemblies were chosen to reflect really common practice here in Ontario. So they're not an average, they're sort of looking at how people are building low rise and building up that model that way. The low carbon option was looking at materials that are currently available through the regular sort of retail and wholesale building supply setup here in Ontario. And then the best carbon one was sort of the opposite of the highest carbon. This was looking at the best possible materials. They're all things that people do use to make buildings out of, but they may not be readily available. And some of them are coming from Europe. They're not manufactured here in North America. So the results of that study, these bar graphs, I'll explain the terminology along the bottom. MF is multifamily and CC is code compliant. So those first 4 bars show you the highest, the moderate, the low, and the best embodied carbon for the code compliant model. Then you've got the multifamily high performance, and you can see that the embodied carbon has gone up on the models that actually have emissions, and that's due to the added insulation. Nothing else in the building's changed except adding insulation, so you can sort of see the jump that improving the energy efficiency takes. The other thing that's interesting here is that the 2 bars on the right, the sort of yellow bar and the green bar for the multifamily building, both end up below 0. So they both have an overall net carbon storage. So that doesn't mean that all the materials that went into them were carbon storing. They still have, things like concrete foundations and glass windows and, roofing materials. But overall, when you took all the carbon storing materials and compared them against the emitting ones, those 2 models turned out to have more storage than emissions. And then on the right-hand side, it's the exact same setup for the single unit building. And one of the interesting things is that clearly, in all categories, the multifamily outperforms the single family in terms of its embodied carbon. So, from a standpoint, a policy standpoint, if you're looking to reduce embodied carbon, the larger low-rise units do a better job than the single family. The other interesting thing that comes out of this is even though the embodied carbon rises on the emitting models when the insulation level goes up, you can see that the storage levels also get bigger. So in some cases, if you're using emitting insulation materials, you're going to up your initial footprint. But if you're using carbon storing ones, by adding more insulation, you're actually adding more storage. And so the rest of the presentation is sort of going to focus mostly on those yellow and green bars, in particular the green bars, because that's where we're going to really be able to make a dent in the building industry's emissions. And just to give you a sense of how this might scale out, if all low-rise residential buildings in the US were built to that worst case scenario, and if you looked at the materials for that worst case scenario, you'll see that that's not a sort of made up scenario. There are a lot of buildings being built in exactly that way right now. So at 345 kilograms per meter squared, all the square footage of low-rise residential construction in the US would be adding 83 million tons of CO2e to the atmosphere, which is like adding the emissions from 23 coal plants annually. And then on the other side, if we were to build all of those buildings in that best case scenario with the best possible carbon storage, we would actually be removing 36 million tons of CO2e from the atmosphere, which is like removing the emissions from 10 coal plants. And obviously, if you're going from the worst case scenario to the best case scenario, you're not just storing that 36 million tons, but you're also avoiding the emissions of the other 83 million tons. So there's certainly plenty of reason to be thinking about this and really making it a focus of our embodied carbon efforts. I just want to be clear that what this study was looking at is cradle to gate figures. So I'm not looking at transportation of these materials to a site, and I'm not looking at the site energy inputs either for construction or operational carbon yet. I'll show you those in a moment. And it's not including the end of life impacts. And this is not to say that these aren't important, but for this study, the transportation and construction side is so variable depending on where the building is being built and where the materials are being sourced from that it's almost impossible to average that, and you come up with the same issues with the end of life. So I do think that these are really important, and it is sort of incumbent on us to be thinking about this piece, but it's not the kind of thing that can be tackled in a study like this, where I'm kind of giving a snapshot of an average type building. So those green bars, those carbon storing materials that can take a building from being a sort of major source of emissions to a potentially major source of storage, would include things like sustainably harvested timber. Although I do want to note that in most of those models, or actually in all of the models, none of the structural wood was counted as being carbon storing. And in a couple cases, flooring and siding were counted because it is relatively easy to get guaranteed sustainably harvested sources for those types of materials. Wood fiberboard, exterior insulation, hempcrete, which you'll be hearing more about in the following presentation, cork, rewall, cellulose, waste textiles, straw, bamboo, and a whole slew of different agricultural residues, from rice hulls to coconut and palm kernel shells, and there's a banana leaves. There's a huge range of materials like that. One of the things that I do want to point out on this slide is that the building, the low carbon building, the one that ended up pretty close to zero in embodied carbon, really almost the only difference between that building and the emitting buildings was the use of wood fiberboard insulation as the exterior insulation cladding and cellulose insulation in the walls and in the roof. So just those two materials alone can often take a building from being a fairly high emitter to being very close to carbon neutral right off the bat. And then I guess, I'm used to getting some eye rolls when I talk about, in this case, straw as a real building solution. But I think it is important to take a look and see that in Europe, there are 2 companies now doing very well selling straw-based SIP panels, and that they're starting to do larger and larger buildings. They have a lot of multi-unit and institutional buildings, as well as single-family homes. My own little school here in Ontario, we make our own straw-based SIP panels. That's that green building you can see there. So we prefabricate sections in a shop and take them and put them together on a site. Agriboard is, I don't think, any longer in business, but some version of Agriboard has been kicking around in the US for over 20 years. It's a straw-based SIP panel, so compressed wheat straw between OSB. There are all kinds of formaldehyde-free straw panels. Most of that is happening in Asia. There's not a whole lot of uptake here, but they are quite viable. Stramit and Ecopanly are a compressed straw interior wallboard, and Isostro is an Austrian company that's using ground up straw like cellulose as a blown-in insulation. So those are just some examples of materials that are being used currently. And just to note that, over 2 billion tons of grain straw are grown annually on the planet every year, so that the source material for just these straw options, there's enough carbon stored in that amount of straw to offset all our current transportation greenhouse gas emissions and to replace all current insulation materials. So just to know that this is already growing, people are already planting it, growing it, harvesting it, and what we're doing is eating the seed part and leaving all this potential storage material to either burn or molder. And then just quickly, I'll drop the operational piece of the puzzle into this, and sort of show you these 2 graphs. So these are for the multi-unit building. You can see on the left, the yellow bar on the left is the embodied carbon emissions of that building, and that was the sort of like moderate carbon building. And then you can see that if it's using natural gas, and in this case, the northeastern U.S. Electrical grid for its heat and power, by the time 2051 rolls around, you've slightly more than doubled the embodied emissions, And that building has been a serious emitter of greenhouse gases from the time it was built and all the way through its operation. And on the right, you can see, the potential that exists in combining both storage-based materials. So you can see that this building on the right starts below the zero line, so it's already contained that much carbon when it started. And because it's a high-performance building, it's operating on the Ontario grid, which is relatively carbon-free, and it's a very energy-efficient building. Its operational emissions eat away a little bit at that initial storage from the materials, but by 2051, that building is still a net storer, and it remains that way until early in the 2100s. So I think this is the kind of scenario that the industry wants to be aiming for, that we all want to be working towards, and it involves both thinking about materials as carbon storage, but also making sure that the buildings do perform well and that the energy source we're using for them is green. Very quickly, a couple of buildings that we've built with our school, just to give you a sense that this isn't make-believe, but that people are building this way now. This is an office building in Lindsay, Ontario, that had 71 tons of net CO2 storage in its 2,400 square feet. And here's our little prefab house, and it's storing 24 tons. And you can see from this building that it's completely clad in steel. It has a steel roof. We're not relying solely on carbon storing materials, but wanting to make the case that if you use the carbon storing materials where you can, you'll end up possibly below a zero embodied carbon line. And just a quick note there that this is something that I think we want to do, but I think we have to also think about things like where wood is coming from, where straw is coming from, and how we fit sort of the larger piece of climate change, both resilience and equity into the whole matter. And so with that, I will sign off and pass the buck.
Chris, thank you so much. Really appreciate that. And next we'll hear from Pamela Bosch. She's going to talk about hempcrete, one of the things that Chris mentioned in his presentation. So Pamela, whenever you're ready, just click the share screen at the bottom of the screen. We'll transition over to you.
Can you hear me now?
We can hear you.
Okay, sorry, having some navigation issues.
No worries.
My whole adventure began just looking for non-toxic insulation. And I found that there wasn't a lot that I considered non-toxic. And I thought that since hemp had been growing in Canada for about 20 years, surely they were using the potential of the agricultural waste to make insulation or use the fibers to make insulation. And it turned out that that was not the case. However, I've gotten a pretty extensive education just following my nose in being interested in the potentials of that plant to be used as a building material. So at the time in 2014, the only hemp Batt insulation was from a UK company called Breathe that I could find. Since that time, there's a Canadian company and a US-based company in Kentucky. But the benefits of the plant were so overwhelming and compelling that I kept researching and discovered that most of my searches for hemp insulation, in fact, turned up a product called hempcrete. This screen is just a couple of European examples of ways to use the inner core of the hemp plant. But what I became involved in is using the inner stalk of the plant along with lime to make a monolithic wall system that is packed into forms and ends up regulating temperature and humidity and being made of very simple ingredients. Just the hemp hurd or core, lime, sand, water, and maybe some pigment and possibly some clay. So this slide shows the material that is used in building. If you look at the upper left, it's a cross-section of the stem of a hemp plant. And so around the perimeter, you see where the bast fibers are. They make the plant tall and strong. Those are what are harvested for various products like rope and the insulation and so on. But the inside of the stalk is a open structured pith that delivers the water to the leaves and back down to the roots. And it turns out that that can also perform very well inside of a wall system, much as it does for the plant. So this slide kind of represents the biophilic image or the aesthetic properties that aren't always visible and aren't always of consideration when we look at building materials. I've thrown in a cross-section of a bone because that relates to the final building product, and maybe I'll come back to this. Oops, pardon me. So if you look at both the hurd and the lime, the main ingredients under microscopic examination, you can see where the pits of the plant, or the pits inside the cellular structure, are like wicking agents to wick moisture through the wall, but are also very insulating. And then if you look at the lime, you can see that it also has a very open structure, as opposed to cement, which would be much denser and doesn't have the properties to allow moisture to move through the wall. So that's why returning to this very ancient building material works better than concrete does in preserving the wall. This slide shows really the essential difference and the energy difference between cement and what they're calling pure lime. So if you're calcining lime, which is mined in a rather pure form, and it needs to be about 90% calcium for a building, and this is the highest restriction on the materials, is that you do need a good quality lime. But if you're using that same lime as an ingredient in cement, it's an entirely different chemical process, requires about 80% more energy to calcine that lime along with some impurities, so that you're getting a clinker that can be set with water. Whereas if you look at the center of the slide, pure lime is actually cyclic. It remains viable in a way that is better illustrated by the next slide. So what you're starting with is calcium carbonate or whiting, which is a common material used in industry. It's used in paper making. It's used as a filler, and it's used wherever you want to bring the pH down. So to counterbalance, for instance, acid rain, the effect of rain on farmland, helping oysters cling to the shells where the ocean water is acidic. So in the calcining process, the carbon dioxide is driven off along with a great deal of heat. And that produces calcium oxide, which is highly volatile. It's stabilized by adding water to it. So you have calcium hydroxide, and it comes in powdered bags, and that's what we use to surround the hemp herd with. And then as it sets, triggered by the water, it actually reabsorbs the carbon dioxide that was driven off in calcination. And so this also relates to the end of life, where say you have a hempcrete wall that needs to be taken down. It can be crushed and used again, conceivably, as an agricultural byproduct, or as an agricultural, for agricultural usage, wherever you would want to balance that pH in the soil again. All of this is very speculative, of course, since there is not really an industry that exists using the hemp plant. It's with the 2018 Farm Bill, there are high hopes that we'll be able to grow this plant and also grow the industries around it. Notably, CBDs are the rage. There are a lot of hopes for the health industry. And if it's so, if all the people that hope to grow CBDs have a market for the rest of their plant, this could make it very economically viable. So these are some statistics that I've gleaned from just websites from, for instance, Sunstrand, the only company in the US that's currently has a processing facility for both the fiber and the herd that I know about. I can't really validate their claims, but this is an example of the amount of carbon that is sequestered by the plant. Another study, many of the studies are coming from outside of the United States because we are just getting to, well, for various reasons, plants and illegal. However, in places like India, lime is commonly in use as a building material as it is in Europe, as opposed to cement. And I would just invite you to look at these studies. Some of their methodology for determining how much carbon is captured is represented in these formulas. The European Industrial Hemp Association is a trade organization or a consortium of people interested in hemp, has funded a number of studies that I can point to. And this is one of the slides from that study, demonstrating the energy of production. The farming production, and in yellow, the processing. This, of course, varies depending on your locality, depending on the type of machinery that's used, the fertility of the soil, and how far you are from a processing plant. And this graph showing, comparing hemp fiber to other insulating products. It looks very impressive. Again, from I believe from that same study, demonstrating the thermal performance of hempcrete compared with extruded polystyrene. So you see the moderated temperature represented by the yellow line. Again, more details of that study, which I invite you to go to that source, since there's not a lot of time for me to go into the details, but also I can't claim to represent the authenticity of the information. However, I think that is an issue in trying to upscale the industry, is that there are a lack of studies. So the reason that I don't have a career in this, but I've kind of dropped everything to become an advocate and builder of this model, is because I think the potential for sequestering carbon, for healthy environment, and for inspiring developing markets is immense because of the benefits. The benefits are so compelling, they speak for themselves. And this is a list of but a few of the benefits. In addition to providing excellent insulating material that ends up with a carbon negative product, there are also parallel advantages in maybe changing the way that we build, and potentials for inspiring building around the world where locally available materials are kind of add an economic incentive. This is another study from UK, which suggests that you could lower the embodied carbon even further by using clay instead of lime. Lime is definitely the most energy intensive ingredient in the process, and clay can be used as a binder, or a binder with small amounts of lime has been demonstrated by a company called Canabric in Spain. And New Mexico, for instance, has a lot permits building with clay. I think is the only state in the US that has done that. Another study, Toronto, since Canada has been growing hemp for longer, there is much a better understanding of a few more studies done in Canada. And in fact, Chris Magwood has written a book on hempcrete I wanted to throw in there. Oops, I'm sorry. So this is my project. This is what the Highland Hemp House looked like in the fall. The work continues. Some other ways of applying hempcrete are, besides the infill of the forms, spraying the walls. The Netherlands has built a 6-panel hemp house. The bricks have been mentioned. Play with lime. The infill slide is misleading. I believe that's shopcrete. However, it suggests that we could develop ways of mechanizing this process with machinery. And I believe, have I spent my 10 minutes?
Well, we're coming up on the hour, and we certainly want to leave some time for some good questions. So yeah, if you could kind of
I can wrap it up there.
Yeah. Okay.
All right. Thank you very much.
Pamela, yeah, thank you for presenting that. I know that personally I wasn't too familiar with hemp as a potential insulation and building material. So we appreciate you sharing the research that you've done and sharing your project, which is looks like very much a labor of love and certainly a passion of yours. So we have a few questions that have come in in the chat. Actually, several are coming in. So what I'll do is I'll read those out. The first question is for Chris. And could you talk a little bit more about the R values of the assemblies that were part of the study? I know that there was maybe a table for that. And was cost included in the study, given the fact that some of the assemblies, based on the assembly type, may need a higher thickness to meet the R value of the assembly compared with other insulation types with higher R values per inch?
Yeah, so that was taken into account. Have to refer back to the slide that had all the R values, but they are all detailed there for all parts of the building. And I kept the floor area constant so that the extra thickness, pretty much it only came into account for the walls, was accounted for. So if a building had, say, 12-inch thick walls instead of 6-inch thick walls, the additional amount of, say, exterior cladding was added to that model. So to the best of my ability, they are sort of completely accurate to how those buildings would be built, including thicknesses. And cost wasn't directly part of the study. I mean, because I am a builder, I know that the things I modeled in those 4 that I showed are all things that are relatively cost competitive with each other. And I distinctly left out things like vacuum insulated panels and aerogel and things like that, which I did model in the study, but they are sort of cost prohibitive to use right now. But everything I looked at are things that could feasibly be used, and the costs are within a decent range of comparability.
That's great. And then there's a question about, are there any additional resources, PDFs, online links, things like that related to straw bale? So kind of 2 things on that. This study or this presentation, is stored online. So if you wanted to go back to any of those slides specifically, you can do that. And then I guess a question to the presenters, if they do have a list of links that they would like to share with folks, would they be willing to, not to put you on the spot, would you be willing to post that on the Embodied Carbon Network as a reference that people could just look at and click on?
Well, as soon as my study is finished, which will be very soon, I'll be posting the whole thing, hopefully, with the Embodied Carbon Network. So the full, I modeled over 300 different materials in that. So that whole thing will be available very soon, within probably a month.
That's awesome. And if there's any straw bale information, sounds like there's a desire to have some links. If you have a succinct list already together, that might be helpful as well to post at some point.
If people are interested in straw bale, there's the California Straw Building Association. They have a new book coming out really shortly. There's a lot of really good information out there through regional organizations and books that have been published.
That sounds great. So a question for Pamela, an interesting question about how much land surface do you need to build a given size of the building? Is there any kind of data on, for if your building is X square feet, that equates to, X amount of land acreage to generate the raw materials, the feedstock that will eventually become hempcrete?
Yes, the figures that I've heard are 1 hectare or about 2.5 acres to build a 1,500 square foot building. And again, I can't really verify that, but that seems about right. And then the other part of the question was, how long would it take to grow that? It depends on where you are, but roughly a growing season. A summer growing season. It's an annual crop. And I see the other part of the question is, can it be used for commercial installation? And I've seen a 5-story building done in Italy made out of sprayed hempcrete. but also in Europe where they produce the insulation bats, those have commercial applications as well.
Yeah, and I would point people who are interested in sort of commercial uses of hempcrete to Just Biofiber up in Alberta, Canada, because they have a precast block that's a really great product. It's been in prototype for the last 2 years, and this is their first year of actually sort of supplying projects commercially. But it's a really great way to take all the benefits of that material and deliver it in a really sort of commercially viable way.
Also, companies that are like Sunstrand is just beginning to produce Batt insulation, and last week their orders were filled through August. Certainly there's a lot more demand than there is ability to supply at this point.
Okay. Another question to Chris. So is the carbon sink in Chris's study caused by these materials being byproducts, or from the carbon sequestration of the materials like in plants? If this comes from sequestration, aren't the impacts from Module D supposed to be reported separately and not added to Module A according to the whole building LCA?
Well, this is probably a longer question than we have time for, but yes, they're basically all plant materials. And so my storage figures come from, there are a number of databases that look at different types of crops, and I took 20 samples from those things of each plant and then averaged the carbon quantity in that plant. So that's where that storage part comes from. But in terms of where it's reported in an LCA, the sort of EPD rules kind of changed in 2017 to allow that kind of carbon storage to show up, you know, in like in the model for the products. And you know, well, I've spent a ridiculous amount of time reading everybody's take on this, but you know, really that carbon, especially from those crop materials, is carbon that would have ended up in the atmosphere almost immediately after harvest. And instead, by going into a building, we are putting it away for a significantly long time. And there's a really strong case to be made that storage, especially for where we are with the climate change issue right now, is really crucial to being able to get our emissions down under control. So as a short form, and then the paper that I'll be putting out next month wades into that in much more depth.
Okay, that's great. Question for Christian. You had talked about the challenges with some of the BioClean legislation and how the data behind some of the inputs is just either not known precisely, or that the supply chains are so variable that it is difficult, if not impossible, to deliver the granularity that some of these bills are requesting. So what would your advice be for legislators that are seeking to drive down embodied carbon in a substantial and measurable way, but still be realistic for industry to comply with?
Out of California and Washington and also some other states, I think it's a very important step taken. You know, embodied carbon, I say, is one of the biggest challenges, global warming, so it's something we have to work on. What worries me and what I see as challenges is that when the LCAs and the EPDs are put in a legal context, that new descriptors are invented. I think facility specific is one of them we haven't seen before, which is difficult for industry to comply with. Other discussions is what averages are we looking at as manufacturers of EPDs and LCAs? We always look at the weighted averages that we deliver. So what is the average of the product that you pick up on the market as a customer? We simply don't have the money or the data to supply what is required. So I think to move forward, I think we should work with the standards, the recognized standards that everybody's using, and really investigate. I think also some of the items brought up by Chris. How can we make the data better? How can we make the data more accessible? A lot of some companies have done a lot of work, but I think it's important that we make sure we have a framework where a lot of more companies, a lot more materials can come on board and deliver this information that we need.
That's an important point. You also mentioned that, and I've heard this also from several manufacturers, that manufacturers, when they are planning, what EPDs to generate and to even do EPDs at all, they're looking for signs and signals from the AEC community, frankly, that, hey, there is a demand. Our clients, our projects are needing this kind of quantitative information to move this forward. I think that might also be helpful for you, is to have sort of a sustained demand from the design community that is requesting this kind of data, so this data can be invested in and collected and then used. Is that correct?
Yeah, I think it's very important that we work together with the ND community to show that this has value. I think often there's a disconnect from manufacturers putting out sustainability documentation to the market and knowing, hey, did this make a difference? And we're having this discussion in several forums. How do we prove? How do we get the feedback loop to show that this actually had value for the project, for the customer?
Mm-hmm. So maybe time for one or two more questions. Another question for Chris about, did you look at steel in either of the buildings, given that material is used frequently in larger building structures and are quite carbon intensive?
I looked at steel not as a structural material. The high carbon model in those buildings, those samples I did, had internal steel framing, so all the interior walls were modeled with steel, and that was actually one of the things that drove the high carbon building to be so high. But I really focused on low rise, so 4-story and under buildings, because I see those as the place where these types of changes, where we could move very quickly from high carbon emitting buildings to carbon storing buildings with very little change. Like, all of those materials suit that scale of building, and that is actually the scale of building that we do the most of in North America right now. So I know a lot of the attention in this space really gets directed to urban high-rise buildings where it is more problematic to use lower carbon materials, but I think we forget that the vast majority of what we build is low rise, and you're not having to use steel and concrete in the same way in those types of structures, and so they open themselves up to this kind of like change, going from emitting to storing buildings quite quickly and easily.
Great. So maybe just a general question for all of you. Many of the products that you have talked about in the studies are compelling. So what do you think are the most important ways that we can help our clients? What is the most important information that we can be providing our clients to move projects and to move the industry in the way of something that is within the realm of cost possibilities, delivers on the performance, and also delivers the lowest embodied carbon solution, or overall carbon solution, let me put it that way.
Well, I guess maybe I'll jump in. I think for me, one of the most exciting things that came out of my study was that low carbon model that ended up being pretty close to being carbon neutral. And that one was built literally with off-the-shelf products that are available in North America and that are completely cost competitive. And so, I think that to a large degree, we could get to that level where our buildings are sort of at or approaching a zero net embodied carbon footprint without a wholesale kind of change in the supply chain or in the costs. That building was achieved with some really simple material substitutions, like cellulose insulation that's available everywhere, like wood fiber board that's made all across North America. So I think sometimes that, the answer is right in front of us, and we just haven't, considered those options because we haven't had embodied carbon be one of the things that's sort of driving decisions. So I think as soon as it becomes a driver, you start to be able to find the things that are already out there and do a good job for lowering the embodied carbon, and are cost competitive, because they exist now.
I think that is, yeah, just real quickly, since we're right at time.
Okay, I think that's the greatest obstacle to using really simple, sensible materials, is that the way we've always done things is rather complicated, and our culture has sort of an economic setup that doesn't really encourage innovation. And I think it's just time for really radical thinking that ironically includes simplicity as a possible methodology.
Well, I think those are two great sort of ways to close this webinar with. Oh,
can I just?
Yes.
Two short comments.
Yes, have the last word.
I think number one, we have to trust the data. I'm really worried that there's so much information out there on embodied carbon. I think we have to make sure that we get to quality where we can trust the data more. Another thing I want to bring up is I think this discussion needs to be inclusive. I think we have to be careful that the discussion in this forum, especially, doesn't only focus on a new and great materials, but there are a lot of other materials out there that are being used and will continue to be used. And if we just focus on these really great new materials and we don't include also the existing materials that are out there and that are being used and will continue to be used, then they won't be a part of this discussion. I think that would be a shame. Or moving forward with reducing the carbon emission from our building stock.
All great points, and thank you very much, Christian, Chris, and Pamela, for being part of this webinar and sharing your information. A lot of great information here. It's a complex topic, and so we thank you for sharing that. Just one other thing, in addition to these webinars, the Materials Task Force also has a series of discussions with subject matter experts. We're dubbing that series called Materially Important. We're trying to do that every 2 months. So look for another presentation of the Materials Focus Group in a couple months. And in the meantime, we look forward to hearing your questions and you guys sharing your information online on Basecamp. So thanks again for everybody who spoke and for all the participants for listening in.
Thank you for the opportunity.